So thank you all for coming. As he said, I'm an engineer at Google, and I'm going to be talking today about streaming and how it relates to SQL specifically. And so just fair warning up front, this is a fairly conceptual, theoretical talk. I'm going to be talking about sort of the ways that streaming and SQL play nicely together, ways that we meaning kind of all these folks that I've listed here and many more, have been discussing and sort of trying to wrap our heads around how can we cleanly integrate SQL and streaming together. So I'm not actually talking about sort of things that exist today. I'll cover that real quickly. Apache Beam has, as of 2.2.0, has a SQL DSL in it. You can essentially write portions of your pipeline in SQL, and it converts to Beam under the covers and just runs normally as you'd expect otherwise. Other projects that have been involved, Flink has had SQL support for like 2 years or something like that. There was a talk yesterday from both Uber and Data Artisans talking about this. So if you want more detail, you should hunt them down. They essentially have materialized view semantics, which is great. But the main focus of this talk is trying to understand how these two relate, and I think it really helps clarify just what stream processing is in general. So I really enjoy it. And with that, let's get started. So contents-wise, there's really two sections to this talk. The first part, we're going to talk a lot about stream and table theory. How many of you know what I'm talking about when I say streams and tables? Pretty good. Great. That's actually the bulk of the talk. And then at the end, we'll kind of talk a little bit about SQL. So if you probably thought this was going to be SQL all the way through, it's not, sorry. Real quickly, these two sections actually relate to two of the topics in the book I'm writing with a couple friends of mine. I call this out, one, because I can only go so deep in like 40 minutes or whatever it is. We're going to try to sprint through this all in. So if you want to learn more, the book's a good option. Conversely, if you hate the talk, you shouldn't buy the book. So, and there is a book signing at 3:20 today, I think. I don't know how the signups work and things like that, but there are some early release copies with all 10 chapters in it. So let's get started. So to begin with, I'm going to try to give a basic intro to what stream and table theory is, kind of where it's come out of, where I learned about it, cite some places where you can go learn more, and then we'll talk a little bit more about how it relates to robust stream processing. So I learned about this idea of streams and tables from primarily Martin's blog post, but also Jay's later on, where they discussed, they were trying to sort of explain the Kafka approach to things. And the idea was, if you think about how databases have typically been implemented in the past, you've got these tables and there's transactions being applied to them. And as those transactions come in, they're essentially stored in a serialized log and then applied one by one to the table. And that yields then over time this evolving table as sort of we, the consumers of it, observe it. And so really that was really sort of this declaration of, this log of changes is your stream. And the table itself, then, that's your table. And that's sort of, that application of those changes is how you convert from a stream to a table. And this is something the database community has understood for a long time, of course. And then conversely, if you have a table, converting that to a stream is essentially observing the sequence of changes to a table and serializing that into a change log of sequences, like change data capture or how materialized views work, these sorts of things. So it's relatively straightforward stuff, but it was really kind of a nice articulation of how this relates to the things that we were all kind of starting to try to do in stream processing at the time. And it's caught on, I think, really well and really informed the way folks are approaching things in the industry. And so from this, you can kind of, to use a bad physics analogy, you can come up with what I would call a special theory of stream and table relativity, define these things in terms of each other. Streams, the aggregation of a stream of updates over time yields a table, and the observation of changes to a table over time yields a stream. So that's great. It's also useful to understand how these two things exist independent from one another. And the way I like to describe that is that tables are data at rest. They're this conceptual grouping place for data to come together and kind of hang out and be observed. Whereas streams are data in motion. They're bits of data or changes to data that are kind of floating around and moving from one place to another. And we'll get into some examples later on where you can see this a little more clearly. But just keep those in mind for now. So now let's move on to the second part where we're going to relate these to the Beam model. And how many of you know what I'm talking about when I say the Beam model? All right, there's like at least 10 of you, so that's cool. then that's fine if you don't. All I mean by the Beam model is sort of the way that we have historically advocated that folks think about data processing from the Apache Beam perspective. And we've often done this through this sort of cute idiomatic lens of 4 questions. What are the results you're calculating? Where in event time are you calculating those results? When in processing time are those results materialized? And if you're materializing results multiple times, how do refinements of those results relate? I mean, it's okay if you don't know what I mean by this, because we're going to go into this in more detail later on. But if we want to reconcile stream and table theory with the Beam model, we need to answer some questions. And one thing I kind of left out is that the Beam approach has tried to unify the approach towards batch and stream processing, right? Like you can write a pipeline once, and it essentially works in batch mode or in streaming mode. And so why this matters is that streams and tables, as Martin and Jay have talked about historically, was really in the context of stream processing. Batch processing was essentially left out of the equation. So we need to reconcile that. How does batch processing fit onto all of this, and what is the relationship of streams to bounded and unbounded data sets? Because batch processing typically addresses bounded data sets, not these unbounded infinite streams, right? And then after we sort of understand that, it's worth understanding how do those 4 questions and the way that Beam and others address them, how does that map onto a streams and tables world? So to start out with, we'll try to answer the first 2 questions, and we're going to do so by analyzing sort of the classic batch processing paradigm, MapReduce. I imagine most of you are familiar with MapReduce in this room. Is this a fair statement? Okay. So with MapReduce, you have an input that goes into 2 phases, a map phase and a reduce phase, and on the outside you get some output, right? For our purposes, it's actually going to be better to think of these as 6 independent stages. So for each map and reduce, split it into 3 where you've got a read, an actual operation, and then a write. So map read, map write, reduce read, reduce write. And in between those operations, the data exists in some form, right? And so what we want to do is we want to answer, are they tables there, or are they streams, or are they sometimes maybe one or the other? And this will help us understand more how batch processing and streams and tables relate. And with batch processing, you start out with a static pile of data, right? That you then run through your pipeline, and then on the other end you get a new static pile of data. So I think that data is just kind of sitting there resting. It kind of feels safe to say that those are probably tables, right? So let's just assume that to begin with. So then map read reads in this table, scans it in, and it's going to hand it off to the map phase. What does it hand off? Does it hand off a table, or does it hand off a stream? Well, if we want to figure that out, a good way to do that would be to see what the map actually consumes. And also, we're going to just look at the map phase to begin with. We'll deal with reduce later. So a reasonable function signature modulo the syntax error here for a Java mapper would be something like this. So you've got 2 inputs, a key and a value, and then you've got this emit object that allows you to produce 0 more outputs afterwards. And the key thing to keep in mind here is that as the map read phase is scanning in data, it's basically handing off records one by one to this mapper, right? So the mapper gets a record, it processes it, it produces. Then later it gets another record and produces it. And really this is happening in parallel across multiple machines at the same time. And so really you kind of get the sense that from a mapper's perspective, like you're really being fed this sequence of records, right? Like it really feels like a stream, and there's nothing about it that's, you're not seeing a holistic view of the table, you're just seeing one by one. You're getting this stream of things and producing a stream of things on the other side. So I think it's safe to say that map read, after reading in that table, produces a stream that is then consumed by map. And so then what does map produce? Well, we've got this stream coming in, and then we're using this emit object to produce 0 or more elements on the way out. And these elements have keys associated with them, but they're not really grouped together in any way, because you can have, again, many machines all producing elements on the same key. They're not actually grouped together yet, right? Like they're on independent machines. They've been assigned identifiers that may be the same, but really, everything comes in and it's just going out on the other side. And maybe the cardinality changes. Maybe you're filtering and decreasing the cardinality, or maybe you're expanding, doing prefix explosion or something like that, and increasing the cardinality. But it's really just continuing to flow, right? So I think, again, it's safe to say that the output of map is a stream again. And then we get to map write. And what does map write do? Well, let's look at some function signatures. So map write is taking the thing that we get out of map, and then it's preparing the inputs that we're going to pass off to the reduce. So it's taking this stream that we got from the map phase, and it's handing off to reduce something a little interesting. So it's, again, reduce is getting a key as the input, and it's also getting then this iterable of values. And this iterable contains all of the values for that given key. So what's happened here in between, as part of this map right phase, is that we've taken all of those keys across many, many machines that happen to be the same, all those values with keys that were the same, and we've grouped them together. We've brought them to rest at one place, and then we're handing this thing off to the reducer. That sounds a lot like kind of our description of what a table is. It's this conceptual resting place for data. And so I think it's safe to say that map right is essentially taking a stream in and producing a table at the end. And for the sake of time, I'm not going to actually go through reduce in great depth. It turns out it's actually very similar. And if you want more details, you should read the chapter in the book, because there is some kind of interesting subtlety about the way that reduce right works in reduce. But basically, map and reduce, and the map and reduce phases and map reduce are not really that different. It's just kind of the shuffle in between them that does the magic. So at this point, we can probably answer those first two questions. So how does batch processing fit into all of this? Well, tables are read into streams. Streams are processed into new streams until a grouping operation is hit. Grouping turns that stream back into a table, and then you repeat steps 1 through 3 until you run out of operations. In the case of MapReduce, you basically do this twice and call it a day. So what is the relationship of streams to bounded and unbounded data sets? Well, streams are just the in-motion form of data, both bounded and unbounded. As you saw with the MapReduce example, we had multiple places where there were streams within the system, right? It didn't matter that they weren't these infinite streams that we usually deal with. They're bounded streams, that's fine, but it's still data in motion, right? All right, cool. So we've got a kind of a sense of how batch processing works. Now let's dive into how do these for what, where, when, how questions, how do these this approach to robust data processing, particularly stream processing, how does that map onto a streams and tables world? So we're going to go through these 4 questions again. We'll do it one by one. So we'll start out with this first one. So what results are calculated? So what's meant by this is, are you computing sums? Are you calculating histograms? Are you building machine learning models? Like, this is kind of the question that we've always answered with classic batch processing. Like, just what is it that I'm computing? To do this, we're going to walk through some examples. So if any of you have read my Streaming 102 article or seen the Dataflow Model paper, you'll be roughly familiar with these diagrams, but they bear some explaining. Basically, we've got this plot here that's showing 9 records. So imagine that these are data records that are generated by some application. We're building a data processing pipeline, right? Say we're a company that has some new mobile gaming platform. Like, we've got people on their phones that are crushing candy or killing orcs or whatever, and they do this in teams, and each individual user, gets scores at some point in time, and the mobile phone sends those scores to our system, and we want to process them, and we want to compute team scores, right? Something like that. So each of these 9 circles here represents a single user score on the same team. And we're only looking at one team at a time just because the parallelism doesn't really scale well to slides. But so you imagine there's 9 different scores here from different users on the same team. And what we've done is we've plotted these scores in 2 dimensions of time. So there's event time, which is when the scores actually happen. So when the person's on their phone, they actually achieve the score, the phone records the time so that we can then, on the back end, correlate those together with other scores that happen across the world and say, this team within this hour or this day or whatever whatever sort of window of time we care about, this is what their score was. And so if you were to read this from left to right, you'd see that the 5 happened first, then the 9, then the 7, 8, 3, 4, 3, 8, 1, right? So event time is the x-axis in blue. But then when those scores happen, they have to get transmitted from the phone to the servers, get into the data processing system, be grouped together, and then processed. And so there's a lot of sort of disorder that can happen between those times. Some people might have different speed connections. They might go into airplane mode for short or extended periods of time. There may be hiccups in various servers along the way. And so what happens is they oftentimes will end up arriving in a different order. And so that's what this processing time axis captures. This shows you the order in which these records actually are observed by the system itself. And so the 5 was seen first. But then the 7, and then the 3, and then the 4, and then the 8, and then the 3, and then finally the 9, which was actually the second one that happened, right? So these records show up in a vastly different order. So these graphs allow you to kind of understand how these differences relate and what they mean for data processing. So that's kind of the basics of what these look like, and then there's going to be animated versions that add more, and I'll discuss that later. One thing to call out that's also nice to note here is that if everything sort of was happened and was processed immediately, like that would be kind of the ideal, right? Like as soon as an event happened, we processed it. They would all lie on this line. And sometimes you do pretty well at like this 3, but then sometimes you get records that are very late, like the 9. So now, back to make it a little more concrete, the pipeline we're going to look at. This is basically the same pipeline from Streaming 102. We're just doing a sum of integers team scores. So we're reading in from some I/O source, and it'll be returning raw bytes. We're applying a parsing function that's going to parse those raw bytes into a key value pair of a team and a score. And so we're going to have a bunch of independent team score key value pairs, and then we're going to just sum those together by key. So group all those by team, and then sum up the scores, and we'll end up with a single team score. Okay? So we'll do this first as a batch job. So this animation, what it's showing you is basically the data flowing through the pipeline. So that's why the y-axis, processing time, kind of time as we observe it, is scrolling downward. It's kind of like a piano roll sort of a thing, right? And so I'll let it loop here. So we start out with these raw bytes at the top, right? We hit the parse function, and you can see, the data in the stream, they just keep going, right? Like, and so parsing is not a grouping operation, right? It's an element-wise operation. And so the thing I really like about these animations is you can see that sense of like the stream staying in motion. You've got this non-grouping operation. It's doing nothing to bring these to rest. They just stay as a stream, and that's annotated on the sides. We've got a stream, you parse, outside you get another stream. And then they get to this sum operation, and that's where you can see, we're doing a grouping operation. And so what's happening is these records that are in the stream are being brought to rest, and they're accumulating there. And you can see the sum kind of builds up as they arrive. And since this is batch processing, when we finally get to the end of the input, we produce an output. So that's kind of gives you a sense for how streams and tables look for like a classic batch processing job here, right? So let's move on then to some later questions, which start to get into things you care about more when you're doing stream processing over unbounded data sets. So where in event time are results calculated? Windowing is the thing that divides data into finite time-based chunks. It allows you to group together events temporally in a way that allows you to reason about things that happened in some similar context. There's a bunch of different ways you can do windowing. I have 3 common ones here. Fixed windowing basically statically chops up time across the whole data set and at regular intervals. Sliding windows are very similar, but they kind of slide less than the width of the window so that there's overlap. Sessions are an interesting case of, usually they're defined as, you've got some sequence of events that all happened within some amount of time of each other. So you define a gap duration of, say, a minute. And so when you've got like 12 events, all of which happened within at least a minute of one of the other events, those kind of cluster together to create a session. And then after that last one, if there's no activity for more than 1 minute, that would terminate the session. So you've got this burst of activity for a given key, usually a user or something like that, that really captures some period of activity. So they're really useful for reasoning about user activity in a system. And they're very interesting because A, they're defined on the data, like you can't know a priori what they're going to be, and they're also unique per key. So they aren't the same across all keys, right? Like they're really very, very, very data-centric and they differ. So if you want to do windowing in Beam, it's a simple addition of this adding a window into fixed windows declaration. And so in this case, let's window into 2 minutes and see what it does to our animation. Let's try to understand how windowing affects streams and tables. And so you can see this looks really similar to what we had before. The only place that's really different is when we get down to summation. Instead of having a single score at the bottom, you can see we've now got 4 of them chopped up into these 2-minute windows, right? And again, this is batch processing. So even though we've windowed our data, we're kind of looking at it in a temporal way, we don't actually produce output until we get to the end of the input. But the main takeaway here is that windowing really is just a modification on grouping. It's kind of like a secondary key. So that's great. We've windowed things, but if we wanted to run this over an unbounded data set, we can't wait until the end of time to get our results, right? Like we really would like to see our results more incrementally. And so that's when the next question comes in. So when in processing time are results materialized? And so there's really 2 aspects to this. One is there's these things called triggers. Triggers control when results are emitted. As we saw in the original examples, those batch jobs were essentially triggering at the end of the input. Like that's kind of what their implicit trigger was. When we have an unbounded data set, we want a more finer grained control over specifying, when do we want to trigger our results. And there's really kind of two main approaches to triggering. There's kind of repeated periodic updates. So this is kind of what you get with materialized views, like updating every record, or updating once a minute, or updating every hour. And then there's kind of completeness triggers, which that batch end of input trigger is really a completeness trigger, right? So like the input is complete. For streaming, when you want to provide some form of completeness, you often use these things called a watermark, which try to capture a notion of input completeness over time. So how complete is the input in event time up to a given point in time? So a watermark is basically a value of time, like say 1202, and it's an assertion that the system believes that you will never see any new records with event times prior to 1202, because that's where the watermark is. And so again, I kind of mentioned that ideal line before in our graph, like if everything arrived and was processed as soon as it happened, it'd fall on this ideal line. But really, you end up having some amount of skew between when events actually arrive and when they don't. And this watermark is essentially trying to fit a curve around all the records and sort of give you a sense for how time is progressing in the event time domain as it has different, I guess, as the velocity of progress changes over time. A little more clear in the example. So let's go ahead and we'll add a watermark trigger, and we're going to switch to running on a streaming engine and see how it changes things. So in this one, we've got this green line here that is indicating our watermark. And you can see, since we're triggering when the watermark passes the end of the window, what happens now is that instead of waiting until the end to get results, as soon as the watermark passes the end of the window, we treat that as complete. It's asserting that we don't think we'll see any more records that will fall in that window, and we produce a single result like we did in batch. But we do so very incrementally, and you can get this sense of like, if this went on forever, you just kind of have this cascading effect of windows being processed as data arrive and become complete. So that's great. One problem here, we've used what appears to be a heuristic watermark. So watermarks can be either perfect or heuristic. If you have complete knowledge of your inputs, you can provide a perfect watermark. It will be an absolute guarantee that you will never see records earlier than the given timestamp of the watermark, and you'll never have any late data. Many use cases don't work well, or for many use cases, you don't have enough information to create a perfect watermark. If you have mobile devices involved, you're just out of luck. You cannot know everything about all of your mobile users and sort of when their records are going to show up. And so in those cases, you often have to build heuristic watermarks that take into account as much information as you know, and give you a good estimate of where completeness is. And that's what's happened here. You can see that the system thought this window was done, but it didn't know about this record, and this record showed up late. It got included in the sum, but since we'd already triggered that window, it didn't get included in the results, and we produced a result that was wrong. It was 5 instead of 14. And so we should fix that. So one way that you can fix it that the stream and table folks have been advocating, if you've heard of this thing called queryable state, you can do this with Kafka, you can do this in Flink, is anytime you're doing a grouping operation, if that's kind of the final result for your pipeline and you can poll for results, like you can just read directly out of the table and your results are sitting there. And if you're okay with eventual consistency, like as late data show up and they're incorporated and that 14 shows up, then you're fine. You actually don't have to worry about it, right? So it's kind of a nice approach for use cases where all you want to do is poll and query. But for use cases where you actually want a streaming answer, like you want to consume your results as a stream, you want to do notifications or alerts, like it's not practical to poll every key constantly to try to generate alerts. In those cases, you want to get the system actually sort of pushing answers to you, right? And so for those, you need some way to specify what to do in the case of late data. So if we want to do that, I'm going the wrong direction, I am. If we want to do that, then let's move to the last question: how do refinements of results relate? So we're gonna kind of tweak our answer to when and also throw in a how answer. So what we're going to do is we're going to modify the trigger here to add late firing. So anytime a single record shows up, we're going to give a late firing. So we don't expect many. Our heuristic's pretty decent. And we're also going to dictate how those refinements relate. So we're going to now have more than one answer for certain windows. And we want to say, how do those multiple answers relate? In this case, we're going to say we're going to accumulate fired panes. That means we're going to build upon previous answers. So we're going to give that answer of 5, that incorrect answer of 5 first, then a 9 is going to show up, and we're going to accumulate those together and give you an answer of 14. Another option would be to discard the original answer and give you the 9, which would essentially kind of give you deltas, or sort of the changes between each time. And so if we look at what this accumulating version would look like, again, it looks almost identical to the last one. until you'll notice when this 9 shows up, not only do we accumulate it here, but we'll also produce a new result. And we've annotated each of the records as being either on time or late. I'll let it run one more time since we only went through it once. And so you can see with these examples, we've kind of gone through a whole suite of approaches. From classic batch, we've added windowing and saw how that applied to streams and tables, and then we've seen how the various streaming approaches and how consuming tables versus streams differs, and how late arriving data and watermarks and things interact. So with this, I think we can kind of start to frame a more general theory of streams and tables and how they relate to the for, what, where, and when questions. And so this, then, I would postulate is a more general theory of stream and table relativity. So you have pipelines. They're composed of tables, streams, and operations on those tables and streams. You have tables. These are data at rest. You have streams. These are data in motion. And then you have operations on these streams and tables. They consume a stream or a table, and they produce a stream or a table on the other side, kind of eliding the whole multiple inputs, multiple outputs thing. That's fine. It generalizes. And then you have 4 types of operations. You have stream-to-stream operations. These are these non-grouping or element-wise operations, like the parse that we had in our example. These leave stream data in motion, yielding another stream. You have stream-to-table operations. These are grouping operations, like our summation operator in the example. These bring stream data to rest, yielding a table. Windowing just adds an additional dimension of time to the grouping. That's really all it does. I mean, if you get into things like sessions, which are kind of more dynamic, there's actually some interesting multi-row transactional stuff that happens as well, but you can kind of ignore that. And in general, it's basically an additional dimension of grouping. And then we have table to stream operations. These are the ungrouping or triggering operations that we're taking our results from that table and converting them back into a stream. These put the table data into motion, giving us a stream and sort of shaped by whatever triggers or accumulation modes we specify. And accumulation just kind of dictates the nature of how the values within that stream relate. And then lastly, we have table-to-table operations, which don't actually exist because it's impossible to go to rest again without being put back into motion. So this kind of captures in whole like the main core concepts, from my opinion, of how streams and table theory relates to robust stream processing. With that, then, we can finally move to talking about SQL. But again, we're not actually going to talk about SQL directly right at first. We're going to talk about the more theoretical part of things, this underlying thing called time-varying relations. So SQL is built on this mathy thing called relational algebra. Basic idea is you've got these things called relations. They look very much like the SQL tables we're familiar with. They're essentially 2-dimensional sets of data. You've got columns of attributes, and then you've got rows of values for those attributes. Right? This should be very familiar. And then within relational algebra, you've got these relational operators that you can apply to relations. You take a relation, you apply an operator, and you get a new relation on the other side. So in this case, we've got projection. We're projecting down to just the score and time attributes, which means this operation is dropping the user column, right? Should be pretty straightforward. And then SQL is essentially a physical manifestation of this. And so we all know we could write this as select score time from user scores, and it would kind of work as we'd expect. Really cool thing about SQL, or about relational algebra, I guess I should say, is that it's a closed system. There's this closure property that you've got a relation. Any relational operator can be applied to any relation, and you get another relation out on the other side. You don't have to think of well, what kind of format is my data in? Can I use this operator or that operator? All relational operators yield a new relation. This is very useful for making it accessible and sort of simple to use. If we want to consider how relational algebra would work in the context of streaming, really streaming is adding this dimension of time to things. And the key insight here is that relations themselves actually, in practice, evolve over time, right? We've got our example data set here, which is essentially composed of 4 scores, like Julie's score of 7, Frank's score of 3, and then 2 more scores from Julie. And you can see the times that they happened. If we were to query this relation over time, like if we did it at 12 o'clock, none of the scores had happened yet. It'd be empty, right? And then at 12:01, Julie's score would have arrived. And so even though these relations themselves are kind of capturing a single point in time, really they evolve over time. And that's the key insight to how streaming relates to all of this, is that classic SQL deals in classic relations, which capture a single point in time, right? But streaming SQL, what you really want is you want to deal with this thing called time-varying relations that captures every point in time for the relation. So what do I mean by this? Well, we already saw this sort of sequence of classic relations that you get if you query the relation at varying points in time. Well, really, all that a time-varying relation is capturing that full history of things. So if we had a hypothetical system that allowed us to, that operated in terms of time-varying relations, and we said, hey, I would like to select star from the user scores time-varying relation, what you would get back is this, which looks very similar to the above, but instead of being a sequence of two-dimensional relations, we now have a three-dimensional object, which itself is composed of that sequence of two dimensions. And it's, of course, flattened out here because of the constraints of physics. But what this is basically saying is that user scores, here's how it existed over these ranges of time, right? And what's really cool about this is that if we were to apply a relational operator to this time-varying relation, because it's really just a sequence of classic relations, it would be the same as applying that relational operator to that sequence above of classic relations independently, right? And what you would get from that is then a new sequence of classic relations. And that new sequence of classic relations is itself essentially a time-varying relation. This is fantastic because this means that the closure property of relational algebra remains intact with time-varying relations. Even though we've added this dimension of time, literally everything you can do in the SQL world, crazy things like cube and whatever it is, they all still apply just as you'd expect because it's just the same as applying them to a sequence of these classic point-in-time relations. So to see this, let's look at some more examples. So this is our kind of standard input set. So what if we filter it? What if we add a where clause? Let's filter it down to just Julie's scores. Well, it looks exactly as you'd expect, right? Like Frank's scores drop out and everything else kind of looks the same. That's fine. Filtering is something that folks do in streaming all the time. How about grouping? Grouping always kind of gets trickier when you're dealing with streaming. Like this is a stateful thing, right? So let's change this to a group by. We're gonna sum up. We'll group by name and we'll sum up the scores and we'll take the max time. Again, it looks exactly as you'd expect, right? Like here where we finally have multiple scores, well, Julie's scores get summed together and you max the time and Frank's score exists and Julie's fourth score shows up and the time increments and the score bumps up and like there's nothing surprising here at all, right? So this is great, but it's not very practical. Like you're not going to use a system that's going to dump out this massive history of a table over all time. Like it's almost impractical at this level of scale with 4 records, right? So how does this relate to something more practical like streams and tables as we know and use them already? Well, tables is pretty straightforward. We already essentially defined time-varying relations in terms of tables, right? Like a table, so if we were to query this hypothetical system that deals in time-varying relations, if we were to query it with this hypothetical table keyword saying, hey, I know you deal in time-varying relations, but give me a table back because I kind of want something tractable. It would look like this. It would give you essentially the snapshot that corresponds. If we queried at 12 o'clock, it would give us the snapshot that fell within that range, right? And so this should be unsurprising. But the one thing that's kind of cool here is that there's actually precedence for this in the SQL standard already. So if we wanted to see this view of the table at 12:01, we could query at 12:01. But also if we went to query it later, there's in the SQL standard an as of system time keyword that lets you, if you have a temporal table, lets you actually say, hey, show me what this table looked like as of 12:01. So even if we queried it at 12:07, we could still see what it looks like. So this is already a thing that exists in the database world. Like I said, the database community has already largely solved most of this stuff. It gets a little more interesting when you start to look at streams. So what does stream look like? Well, if we query the stream at 12 o'clock, it looked like this, which is relatively similar to querying the table, right? They're both basically empty. The main difference here being that we've got this ellipsis indicating that you've queried a stream, and there's more to come. And if we advance time to 12:01, Julie's score is going to show up. If we compare that to the table, again, it looks basically the same. But if we advance a little more, things start to look interesting. So you can see, the table looks as we expected. It has Julie's scores as of 12:03 and Frank's score as of 12:03. But the stream is actually capturing a discrete evolution of things, right? Like it shows you, well, at 12:01, Julie's score was 7. And then we got Frank's score at 12:03. And then at 12:03, Julie's group score was 8. So you can see these two are starting to diverge here. And as we advance time more, you can see again, they start to diverge. And this is a key point. there are a lot of folks that, or there are a lot of systems that have advocated that, if you want to deal with SQL and streaming, just treat streams like tables, it's fine. They're the same thing. And in as much that the underlying conceptual, unifying concept is time-varying relations, and relational algebra still holds within that, that's true. But as you can see here, they're really very different beasts. And so it's just bear in mind that there are differences here, and understanding those differences is really going to help you, do things properly and choose to use one or the other where it makes sense. Just assuming that they're the same, you're going to kind of have a bad day if you don't notice that they are actually kind of different. So to summarize, how do time-varying relations relate to streams and tables? Well, tables capture a point-in-time snapshot of a time-varying relation, and streams capture the evolution of a time-varying relation over time. All right. Great. Let's actually get to talk about SQL language extensions. This is probably what you thought this talk was going to be about. I have all of 2 slides for this. So when do you need SQL extensions for streaming? When we went through this trying to sort of discuss how are we going to approach this, we really wanted to try to minimize the amount of extensions that you would have to deal with. Extensions are no fun until you get things into the standard. They only work in certain areas. And so the key to this is noting that if you can come up with good defaults, you often don't need extensions. And so whether you need them extensions depends a lot on how the output is consumed. If you're consuming it as a table, you rarely actually need extensions, right? SQL is a very table-biased system. It's developed over the years as a table-oriented approach, so you generally don't need SQL extensions, even if you're dealing with tables kind of evolving over time. If you do want to consume data as a stream, then extensions are sometimes needed. And this is kind of a summary of most of the extensions you might care about. We've already seen the explicit table and stream selection for being able to select what type of view do I want of my data changing over time. But even better is having sane defaults so that you don't have to choose. If all the inputs are table, a reasonable default is probably an output, having the output be a table. This is what we're all used to. If any of the inputs are streams, it's probably reasonable to have the output be a stream. And if for some reason you want one or the other, then you can explicitly specify that. When you're dealing with streaming data, there are some extensions that do make sense. So timestamps and windowing. Often you want to deal with things within windows, right? You can do basic windowing in SQL. You can just mod a timestamp and do fixed windowing, essentially. But if you want to do anything fancier, like sessions, where you've got these dynamically growing, data-driven windows, I don't know how to express that in declarative SQL. If anyone here knows how, I'd love to hear it, but I don't think you can. And so in that case, it's useful to have windowing extensions like session that let you say, here's a data set, turn these into session windows for me. And it can do all the complex math and multi-row transactions under the covers to make it happen. So Apache Calcite, Apache SQL parser, has windowing extensions added by folks in the Flink community for fixed sliding and session windows. I think they call them tumble, hop, and session. And that's basically kind of all you would need as far as windowing goes. And then other time, when you're actually consuming data as a stream, you may want to explicitly describe what the shape of that stream should look like. We saw in our example how we chose different triggers to get different effects of what that stream looked like. It'd be great if those can just be implicitly defined by the characteristics of whatever sink you're storing your data to. Sometimes it just makes, if you're writing to HBase, it's probably, there's probably a certain approach that makes sense. So maybe that could just be specified by the sink itself. You can imagine querying them outside, or configuring this outside the query. This is basically what K-Streams does, and I think Flink is also supporting this. So I'm running a pipeline, but independent from the SQL I've written, just here, I want you to repeatedly produce events every 1 minute, that kind of a thing. If you want to do it within SQL itself, then you're going to need to add something, and we've proposed something like this emit keyword, where you can say at the end of the query, I'm going to do some selection and emit it into a stream. When? Well, either repeated updates, as I'd said before, after 0 seconds if you want every record, kind of like materialized views usually work, or every minute, or every hour, whatever cadence makes sense for you. Or if you want completeness, if you want to do the watermark thing like we were, where you get more of a batch style kind of single answer per window, you can say, emit when the watermark is past this given timestamp column, which is probably the end of the window. Or maybe you might want to mix those up to do like we did in our last example of having a watermark followed by some kind of late data trigger or whatever. You can imagine doing that. And that's really kind of it. In most of the common cases, you wouldn't really need to use extensions. And as I note down here, most of these are theoretical. None of the emit stuff's been implemented. There's some windowing stuff in Calcite, but a lot of this is just sort of conjecture of what would make sense and how we could do this in a sane way that isn't overly complicated. And so that's really it. Like, to summarize, we looked at streams and tables and how they relate to one another, defined them independently of each other. We looked at how streams and tables relate to the Beam model and robust streaming data processing. We looked at time-varying relations and how they capture the evolution of a relation over time, but still leave relational algebra with this nice closure property, and then looked at some SQL language extensions that would allow you to deal with these things on a day-to-day basis. So slides are sort of here, although I didn't update this because I did give this talk at Big Data Spain, so it would be Streaming SQL Strata SJC. If you want to see the Google Doc where we've been kind of discussing all of this out in the open, it's here. It's kind of a mess. If you read the whole thing and read all the comments and grok all of it in your head, you will be able to construct a picture that looks roughly like what I said here, but it's not cleanly in the doc. Sorry, I haven't gotten around to cleaning it up. This streaming in Calcite is Julian Hyde, the founder of Calcite, his original vision for streaming. This is what really got me excited about Streaming SQL originally, so it's kind of fun to read. He also wrote this doc, Streams, Joins, and Temporal Tables, which will, if you want to explode your mind, read that. It's fun. If you want to know more about the Beam model stuff I talked about, I have these 2 blog posts from Streaming 101 and Stream 102. These, of course, are the projects, and then I'm on Twitter. That's all I got. Thanks for coming.